Okay, thanks a lot, Veronica, and hello, everyone, again. Let me begin by giving a quick recap of what we talked about last time. So we talked about this, or I constructed this hybrid black hole in this JT flat space setup. This picture here represents the Euclidean version of the black hole, and this is its Lorentzian continuation. We discussed what what I'm drawing here is the black hole spacetime, but there's also matter propagating on the spacetime, and you can think of it as a collection of entangled particles, either going out of the black hole. Well, entangled particles look like this. And there are also particles falling into the black hole. That one entangled with this one here. So what this is meant to describe is a black hole in thermal equilibrium with these flat space CFTs, which I've been calling baths. I also talked about this, this issue of sorcery. I'm going to try to draw a pentagram. Yeah, there you go. It's a good one. And where it's, which is the fact that gravity is able to evaluate this trace, this partition function trace over e to the minus beta h using a single solution, namely the Euclidean black hole solution. And from that single solution, it predicts a large number of black hole microstates. The idea is that the confusing thing is that we started by trying to compute a trace. So one would have hoped that in this calculation we would see all the different elements of this trace or the microstates being added up, but nevertheless you don't see that. And there was a question from last time about the relation between this JT black hole and higher dimensional black holes. I just wanted to make a comment that I forgot to mention this last time, but JT gravity can actually be viewed as the near horizon geometry of, say, ADS Reisner-Nordström, where the JT metric is the component of well, it's the components of some two-dimensional factor of the space where you have like dt plus a radial coordinate squared, I guess, and phi is meant to be the volume of the transverse directions. This story has been made precise in many different papers. Maybe I'll add some references on the Slack later. Something else I wanted to note, which is that we discussed the thermal entropy of a black hole, which was the thing that we obtained from this sorcery business. And we got, using the Gibbons-Hawking procedure, that the thermal entropy is given by the Bekenstein-Hawking entropy, which is the area of the horizon divided by 4G Newton. The comment I wanted to make was that we're talking about a wormhole. So at some point I'm going to discuss or I'm going to make mention of the thermal entropy of the wormhole. You should think of this thermal entropy. Well, for the wormhole, one expects the thermal entropy to be double the thermal entropy of a black hole, because a wormhole is like two black holes, at least as seen from the outside. It looks like it has two separate event horizons. And so the right notion for the thermal entropy of a black hole is twice the Bekenstein-Hawking entropy. Okay, so that was a recap and one quick note. Any questions on this?
Hi, sorry, I have a question regarding that final point about the wormhole entropy, because at least my intuition for the black hole entropy is that you have the Hartle-Hawking state, which is a pure state, but then when you trace out one of the components, you get the thermal entropy on just one of the sides.
Mhm.
Wouldn't the wormhole be with the two sides and therefore be a pure state? And shouldn't it have zero entropy? Or is my intuition just wrong?
No, your intuition is spot on. I did not, good. So the more precise, okay, I did not derive this fact for you. I was just stating it as, I was trying to give some physical intuition that you should think that if you were to compute the thermal entropy of the wormhole precisely, you should get something like this. Okay, but how should one compute the thermal entropy of a black hole? Well, sorry, of the wormhole. Let's first let me state the case for a single black hole. For a black hole, what we did is that we considered the thermal field double of that black hole with some copy of it. Okay, and then we got the thermal field double, which is what's on the top of the slide. And then when you trace one, you get the thermal entropy. But now to get the thermal entropy of a wormhole, you have to consider two wormholes. And then you would have a thermal field double of these two wormholes. So it would look like you have four black holes.
Yes, thank you. That makes a lot of sense. Thank you.
Yeah. And then in that calculation, if you do it carefully, you'll find this twice times the Bekenstein-Hawking entropy.
Mm-hmm.
Yeah.
Ahmed, before
Yes.
you get back, sorry to interrupt, but before you get back into the flow, it seems that lots of people are hearing this high-pitched background noise. I'm wondering whether you could try a different microphone or something. Maybe the locals can help me troubleshoot, but if we could sort it out before you get to the lecture very quickly, that might be.
Okay, let me see.
Can do. If not, then I think we'll just.
Well, I can try to hook up to the microphone of my iPad, but the annoying thing there might be that you might hear the tapping when I write on the iPad. But should we try that and see how people like it?
What do people want actually? You guys, how bad is it? There are a couple of complaints or comments in the chat.
Tapping is better than high pitched. Okay, we can try it.
Let's give it a try, maybe.
Okay, let's try. Okay, so
I think it might. I have a theory that it might have to do with the Zoom background noise suppression in the Zoom settings, but that might be too annoying to try out. I don't really know what it's from though. Someone could Google it later.
Actually, let me.
You want to unscreen share it? Or?
No, I'm fine. I just want to try something first.
Recording in progress.
Not hearing anything.
Yeah. Well,
Do you hear the high pitched sound now?
No.
Much better.
Oh, perfect. Okay.
Okay. This. Let me see what happened. What did I do? Oh, sorry. So this is the mic of my iPad, but I'm going to try something. What about now? Do you guys still hear the?
That's worse. Much worse.
Okay. Okay. We'll just do this. Can you guys hear me?
Yeah.
Yes.
Perfectly. No.
Okay.
Okay. Now I have to read sharing. Oh, lovely. Okay, you're all set. Thanks so much.
Okay. Here's the tapping. Is the tapping fine?
Great.
Mm-hmm.
Okay. Okay, good. So any more questions about
yeah, can I ask a question?
Of course, go ahead.
About the sorcery. So it seems that the only reason that you have a single classical solution calculating your entire partition function is because you assume that the path integral can be solved by the on-shell contribution. And so that obviously just gives you a single solution. So what justifies you approximating the path integral with the saddle point?
Excellent question. We don't know. It's a guess.
Okay, so then the statement is the sorcery comes up because you're making this guess. So it's not really sorcery.
So we made a guess, and we got an answer, and the answer is very reasonable. Like all indications. So you might have thought that, okay, this restriction to a single saddle point is not well motivated, and that and maybe it leads to other paradoxes elsewhere, that it gives you wrong answers for other things. But this answer seems to be the correct answer.
Okay. Usually when we do the saddle point approximation, we have some large prefactor in the exponential, right? But here we don't have such a thing.
Oh, we do. We have 1/g Newton. So the
right, but we don't have the ability to take that as small or as large as we want. It's something that's fixed by nature. It's not like it's not like in quantum mechanics when we want to take the classical limit, then we can make h bar smaller and smaller and smaller. Here we just have a fixed value of g Newton.
Yeah, but it's much it's the highest scale that we have. It's the smallest number that we have in the problem. The Planck scale is the highest scale that we have. In other more controlled models like an ADS CFT and so on, the Newton's constant is actually a parameter. It's like n of the boundary theory, the size of the gauge group, and so yeah.
Okay, thank you.
Yeah. Actually, I missed who was asking that question. I didn't have my Zoom open.
I was.
Was Peter? Okay. All right. Thanks. Okay. Any other questions about last time? Okay, so let's move on. Next, let me give a quick recap of computation of von Neumann entropy. I'm sure you guys have been steeped of how to compute entanglement entropy from the other talks. The statement is that given a CFT in the vacuum on flat space, there's a very nice formula for computing the entropy of an interval. Say the interval is between 2 points x1 and x2. Then the formula is, there's C, the central charge, over 3 times the logarithm of the length between x1 and x2, divided by these cutoff factors, which come from renormalizing the twist fields, which you use to compute to derive this formula. What these cutoffs do is they remove the infinite amount of entanglement across the 2 endpoints. The entanglement entropy is strictly infinite. It's not a very nice, it's not a very physical observable unless you regulate it in this way. And the reason why it's infinite is because you have a CFT and you have excitations at all length scales as you go all the way down, and you need to cut that off. You can choose to work in light cone coordinates, and you'll get something like this. Notice how each cutoff is you have a cutoff for the 2 light-like directions at each point. Okay, so that's, I'm hoping that everyone is familiar with this. Okay, now let's talk about applying this formula to the black hole background. So let's discuss computing the entropy of an interval on the black hole background. Let's consider an interval that starts in the black hole region and ends in the bath region. So the first step is to pick the interval, to pick the endpoints. The second step, another thing you need to do as part of the first step is to fix your cutoffs. Okay, and the cutoff you need to fix is you need to sort of define a physical cutoff, and the invariant thing to consider is the proper distance in the physical metric. So here's the cutoff at 0.1. You just you choose this to be the metric at 0.1. By the metric here, I just mean the proper distance between the endpoint y1 up until this point here. Okay, so it's just a proper distance of that small segment. And similarly, you'll have something on the other side. The second step is here we don't have a CFT on flat space, but we can get around that by first mapping to the CFT on flat space by going to this W frame that we talked about last time. So then that will map this interval to some interval here. It's the same place. And then because the state is the vacuum in the W frame, we can just use the entropy formula that we just discussed on the previous slide. So you'll get the separation along the plus direction times the separation along the minus direction divided by the cutoffs. Okay. The third step, what you need to do is, well, the issue here is that these cutoffs they're not physical cutoffs. They're the cutoffs in the W coordinate system. And so what you need to do is you need to express those cutoffs in terms of the cutoffs in the physical spacetime. The way you do that is by relating the metric in the W frame to the physical metric. So this metric here in the W frame, this is supposed to be epsilon W plus, epsilon W minus. And this metric here, now I'm first considering the bath, the point on the bath, or in the bath. This metric here is epsilon Y plus, epsilon Y minus, which is the proper distance, or the proper length, let's say, in the physical metric, the physical bath metric. And here I'm not doing anything fancy. I'm just doing a coordinate transformation, and I'm just multiplying epsilon squared divided by epsilon squared. By the way, this epsilon is the holographic renormalization epsilon. It's the distance from the asymptotic ADS boundary. It's just the radial distance. Okay, so that was for the bath, and then we can do the same thing in the bulk, for the point in the bulk. And again, you do the same trick. And now this here is the physical metric in the bulk. So this now would be epsilon Y plus, epsilon Y minus.
Ahmed?
Yes.
Could you explain again? We went from a formula on the previous slide that had a single epsilon for each side of the interval. How did that turn into epsilon Y plus and epsilon Y minus? What are those two different symbols representing?
Good. So let's go here. So already, this thing was, so essentially what's happening is that, let's say that this distance here is epsilon 1. What I'm doing is that I'm breaking this up into segments along the null directions. So this is going to be epsilon 1 plus, epsilon 1 minus. So the statement is that epsilon 1 squared is equal to epsilon. Wait, I'm not doing this right. Well, I'm just.
Well, it's null direction, so it won't be the Pythagorean theorem, right?
Yeah.
I believe you that this is the right formula.
I'm just doing this. dy plus dy minus is equal to, like, the metric is dt squared plus dx squared, right?
Okay, thanks.
I'm saying a distance epsilon here, or epsilon squared here is like a distance epsilon plus epsilon minus here. That's all I meant. Okay. Any other questions? Okay. Now let's apply this to something interesting. Let's apply this to compute the entropy of the Hawking radiation. So let me see, how should I? Okay, so the first statement, let me define what I mean by the Hawking radiation. I'm going to call the entire bath, or at least almost the entire bath, the Hawking radiation, and I'm going to use the symbol B for that. So that's supposed to be these two blue segments, and I'm going to study the evolution of the entropy of the union of these two blue half spaces as a function of time. And by time here, there are many notions of time in this spacetime. By time here, I'm going to consider the one where I evolve both sides upwards in a symmetric way. Okay, I could have chosen a time which goes like this, but that's a symmetry of the spacetime, and also of the quantum state, and so the entropy won't change under that kind of time evolution. Okay, the claim is that the entropy will grow linearly for all time. Let me first give you a schematic argument. Schematic argument is that there are two processes that happen. So the black hole is exchanging radiation with the bath. One thing that can happen is the bath can capture one of the outgoing Hawking modes, like this green one. Okay, so B captures one member of the entangled pair, let's say. Okay. Another thing that happens is that B loses a member of an entangled pair. Okay, that's this fact, that the fact that this red particle here, it fell in and it escaped. It's no longer contained in B, but its partner is still in B. Okay. By the way, I've drawn the green lines and the red lines symmetrically about the horizon. That's what this state looks like. This state is at least if you use the free particle or sort of free field theory intuition, it really does look like you have, the particle here is entangled with the particle there, and this one here is with that, and so on. It's entangled symmetrically across the bifurcation surface. Okay, let me just finish the argument, and then I'll take questions on this. And now the claim is that this process, or this Hawking radiation, is generated at a rate given by the temperature. Okay, that's what the temperature means, and therefore you expect that since the temperature is constant, you expect that the entropy of B due to these processes would be proportional to the temperature. So that's 1/β times the central charge, which is the number of species. Oops. Times the time. And so the entropy should continue to increase linearly for all time. Any questions about this quick argument?
So the way you've defined this, does this have a natural endpoint then? Because I guess if you have an evaporating black hole, like the mass will eventually go to 0.
Did you confirm? Oh, sorry, were you saying that we do have an evaporating black hole, or
Or I'm
that we
asking,
don't?
like, should we think of it in the same way? Because it seems like we don't have this mass that will eventually go to 0.
Good. If we didn't have this incoming radiation from the bath, then this black hole will gradually shrink, and its temperature would actually go down, I believe, not up, because it's an ADS, and it'll eventually evaporate away. But what we actually have is that the mass stays constant, the temperature stays constant for all time. So this process just continues for all time, and the entropy grows arbitrarily large.
Okay, so I guess, like, is there some way to turn it off if we do want it to evaporate? Or
Yes, you can change the quantum state in the bath. So I can, at some point here, say I can switch off. So here, well, first let me emphasize that the state has a lot of radiation coming in from Scry minus, right? We can choose a quantum state where these guys turn off at some point. Then there won't be any, then there won't be radiation coming in here. And so you'll only have outgoing radiation. And then you can actually show that the black hole does indeed shrink. And well, I mean, we don't understand the final moments of evaporation when it's about to disappear, but you can show that it actually decreases for a very long period of time.
thank you.
Yeah. Any other questions? Okay, so that was the schematic argument, but we developed all this machinery of entanglement entropy and so on, so let's use that. So let me give you the more careful argument. So here's the space-time again. Let me see. You can use the fact that you have a global pure state of the matter fields, which would say that S B bar, I guess I should define what B bar is. So this is B, this is B bar. B bar, they cover the entire Cauchy slice from one spatial infinity to the other spatial infinity. And because the entire state is pure, the matter state is pure, this is 0, and therefore S B is equal to S B bar. Okay, and so now, so the entropy of B is simply given by the entropy of a single interval, and we just discussed how to compute the entropy of an interval. You can run through that machinery, and you get this answer. We're not going to go through the steps, but if you take this answer and you expand it at late times. It's blue. If you study this at late times, so when U is very large, the Cauchy becomes an exponential, log of an exponential, well, the log cancels the exponential, and so you get 2 pi over 3 times C times 1 over beta times U, okay, which is great, exactly what we wanted, plus infinity, which I'm going to ignore. Okay, now maybe we should talk about this. Where does this infinity come from? Well, it comes from the cutoffs, right? This is minus log square root like epsilon L epsilon right. That's what I meant by infinity. But this comes from sort of the short scale, or the short scale entanglement, or short range, sorry, it's a better term, entanglement. across the endpoints of the interval. Another observable, well, another kind of entropy you can consider to that would sort of capture the long range entanglement is something like S rho hat B at time U minus S rho hat B at time equals 0. This thing will be mostly this plus some small finite terms. The point is that this cutoff term, the cutoff term, this divergence here, is independent of time. Okay, any questions about this? Okay, good. So that's the answer. Next, let me talk about how this very sort of innocent looking result breaks physics. Okay, so no questions. Let's go to the big stuff.
Sorry, Helco, one really quick question. Do those small finite terms, I assume, okay, so the cutoffs, maybe the cutoffs do actually change with time because of the change between the W and the Y frames? Is that what gives you the small finite terms? Like if the cutoff is supposed to be the same proper length at different times, does that look different in the W frame than in the Y frame or something like that?
Let me see.
This calculation is done in the W frame, right?
This calculation is first done in the W frame, but then you transform back to the Y frame. I think the only comment, I don't know how much I have to say about this, these small finite terms, but the only comment that I'm making is that if you just consider this quantity here, the cutoff dependence in the Y frame cancels. That's the main punchline. Okay. Moving on. So I'm going to consider three scenarios of increasing level of wishful thinking. And I'll describe the pros and cons of each. And the first scenario to take is the result that we got sort of at face value. This scenario is often described as saying that you have a remnant or a bag of gold. The idea is that you simply trust these results that we got, which I'm going to now I'm going to use the convention of calling B just rad and B bar the wormhole. And on the bottom left, I have this is an entropy versus time figure where I show both entropies growing with time for all time. I've drawn that it starts at 0. It doesn't actually start at 0, but it starts at some small value. I see that I forgot to erase the note that I left for myself to define this thing, which I'll do in a second. So these entropies grow for all time. And this horizontal red line is supposed to represent the thermal entropy of the wormhole. And at some point, this von Neumann entropy that we calculated exceeds the thermal entropy. That time I will call the page time. And I'll say more about this later. The sort of the picture or the cartoon you should have for sort of what's happening as a function of time is that you have a lot of these green modes in the two bath regions that are entangled or continuously getting more and more entangled with the radiation that's stuck inside the black hole. So here I'm looking at the quantum state of the matter on some late time Cauchy slice. Okay, so any questions about this? Okay, very good. Let's talk about the pros and cons of this scenario. So the pros is that you have what you can call global unitarity, right? The state on these Cauchy slices as a function of time is pure or remains pure. So let me just say the global state remains pure. So it looks like we don't need to introduce any new physics. It's all good. And the radiation purifies the wormhole. The cons are a lot. The first con is that it contradicts the central dogma. In particular, this arbitrarily large entropy for the wormhole suggests that there's no upper bound on the number of states at a given energy or below any given energy for the wormhole. Right, so I'm going to go back a slide. So you can put as many excitations inside the black hole interior, and all of those would seem correspond to different microstates of the black hole. So it exceeds the Bekenstein-Hawking entropy. However, in ordinary systems, you expect that the maximum von Neumann entropy at a given expectation value of the energy is just a thermal entropy. This is a theorem. You can actually try to prove this. It's not too hard. You can try to find. So you suppose that you have a density matrix that gives you some expectation value of E, and you can try to pin down the matrix elements of this density matrix that would maximize the entropy subject to that expectation value of E, and you'll find that it's going to be the Boltzmann distribution. Okay. Finally, this result is not consistent with holography. In holography, I should be allowed to replace an ADS spacetime or an ADS black hole or wormhole with two quantum systems on the two boundaries, left and right. And well, these are supposed to be ordinary quantum systems, but this duality would be in danger if a wormhole doesn't behave like a quantum system, or a black hole doesn't behave as a quantum system. Any questions about the scenario, remnants and bags of gold? Okay, next, let's talk about information loss. The idea here is to to trust the answer for the computation of the entropy of the radiation, but to distrust it for the entropy of the wormhole. The idea is that maybe somehow due to some hidden power of gravity, that maybe it gets fixed. And that it gets fixed and it maxes out at twice the thermal entropy, or well, rather thermal entropy or twice the Bekenstein-Hawking entropy. Like you would need something like this in order to salvage ADS CFT. So far, I didn't tell you what would do this. I'm just considering this scenario. You can also, within this scenario, one would say that one does not have a sort of similar expectation that would fix the entropy of the radiation, because A, there's no gravity in the bath, right? So this the radiation is purely in the bath. There's no gravity there. And also in principle, I mean, the bath is an infinite quantum system. So there's no upper bound in principle. And moreover, the calculation is the techniques that we considered for computing the entropy of the bath. They apply purely in the bath region, sort of far away from gravity, from the bulk. So it seems at least far-fetched that the gravity in the bulk can have an effect on the entropy of the radiation. So in this scenario, one would get something like this picture here, where the let's see what color should I pick, where the entropy of the wormhole would grow with the radiation up until the page time, and then it would transition and become constant. It's maxed out, it can't get any more entangled, but the entropy of the radiation continues to grow for all time. Okay, so that's the information loss scenario. Now let's talk about the pros and cons, if there are no immediate questions. Okay, so still on the information loss story, the pros is that it's consistent with the central dogma. In particular, the number of states is still e to the whatever S Bekenstein-Hawking, or maybe 2 S Bekenstein-Hawking. So that's great. As for the cons, well, it conflicts with the central dogma. By that I mean it conflicts with a different aspect of the central dogma, namely it leads to non-unitary evolution. You get information loss. And to see that, consider the entropies just before the page time, well, not just, but before the page time and also after the page time. So if you look at before the page time, the entropy of the radiation is equal to the entropy of the wormhole. And so it's consistent to have that the total entropy is 0, that the radiation purifies the wormhole. And so the state of the combined system is pure. However, for T after the page time, the radiation entropy is greater than the wormhole. And so you can prove that this means that the entropy of the union has to be greater than 0 using subadditivity. Okay? And so the total state is mixed. So it seems like what's happening, going from before the page time to after the page time, the state is evolving from a pure state to a mixed state. This is non-unitary evolution.
Excuse me.
Yes.
I think it's something you already said. I just missed it. What argument did you use to claim that the entropy of the wormhole just saturates at the Bekenstein bound?
I just declared it. I said, let's just suppose. Well, the wormhole it's in a theory of gravity, and so I'm just going to say maybe we don't understand the rules. So let's make the simplest next modification to the story. And I'm just declaring, I'm just saying, let's just suppose that there's some effect that comes in and it fixes the entropy of the wormhole. I'm assuming it. Is that clear?
Yes, it just I find a little complicated to understand why if the entropy of the radiation keeps increasing because you are throwing in the radiation more partners of Hawking radiation, then how the wormhole one would not increase instead.
Yeah,
I guess just a supposition to have like a clear picture of the possibilities that we have. Is that the idea?
Yeah, but also in some sense, I'm constructing a straw man, basically. I'm just considering hypothetical situations, and then I'm going to tear them down later.
Thank you.
Yeah. Any other questions? Okay, next. The next possibility or scenario is unitarity, is to say that the two systems, wormhole plus radiation, they evolve according to some unitary time evolution. And the initial state here, the initial state here starts off with a state of low entanglement, which is actually true in the thermal field double is a state where you have sort of very special arrangement of entanglement where at t equals 0, the entropy between W and R is actually relatively small. And then as you grow, as you evolve in time, everything mixes and so on, and so you expect the entanglement to grow. Here I'm just arguing this and just using general principles, but I mean we already saw how the entropy grows between the wormhole and the radiation, and this evolution is subject to some constraints. The first constraint is that the entropy of the wormhole and the radiation has to be the same for all time. They also have to be bounded by the minimum of the thermal entropy of either the wormhole or the radiation. For the wormhole, that's twice S Bekenstein-Hawking. For the radiation, that's infinity because it's an infinite system. So really, this is really the tighter bound. And the other thing is, well, what this means is that the entropy of the radiation at times greater than the page time must equal to the thermal entropy of the wormhole, which is just twice the Bekenstein-Hawking entropy. This kind of analysis, and a much more careful one in a slightly different setting, was first done by Don Page, and that's when this time scale comes in, where it was well, I doubt that he called it the Page time. I think usage of this term started in 2012, where it's a time at which the von Neumann entropy of the radiation is equal to the thermal entropy of the black hole. That is defined by this equation. And at this point, subject to these constraints that come from general quantum principles, the entropy has to transition in this way. Yeah. The point behind all this discussion was just trying to motivate this picture that entropy first grows because there's room for the entropy to grow, and then it saturates once you max out the entropy of one of the systems. Any questions about that? Okay. Again, let's talk about pros and cons. Well, the pro is that it's fully consistent with a central dogma. The cons is that it's kind of a tall order. It's not clear how it can be achieved. The central question is, where does the semi-classical treatment, the derivation that we went through, where does that go bad? In particular, I mean, this derivation happened in, or rather the problem occurred in a regime of sort of long times and low energy. We never needed to consider, trans-Planckian collisions or anything like that. In particular, what this means is that quantum gravity effects are will be small, and this means that they won't be enough. So they're not enough to fix the order 1 error. Effect, let's say, right? This problem that we're finding is an order 1 problem. This statement here that proving that these small corrections cannot change the answer, this famously goes by the name small corrections theorem due to Samir Mathur. So this statement here, the fact that it's so puzzling, where sort of corrections would come from, is sort of the statement of the information paradox. That's why it's a paradox. It seems like all the steps are sort of trustworthy, but the final conclusion is nonsense. And there are more problems. One is how to see that information escapes. Suppose you throw something into the black hole, you expect it to come back out, but it doesn't come out. Furthermore, something I'll discuss in a little bit is that unitarity seems to lead to a breakdown of space-time. That's the firewall paradox. So even if you assume unitarity, so you can try to come up with sort of the minimal set of assumptions that would need to be satisfied in order to give you unitary evolution, and you'll find that they lead to crazy outcomes, which is the firewall. But before I transition to that, are there any questions? Okay. So let's talk about the firewall paradox. So let's consider the system after the page time. And let me state two postulates. The first postulate, postulate 1, is sometimes goes by the name of no drama, which is the statement that the state at the event horizon of the black hole is empty. It's the vacuum state. Remember, we had this 0 tilde state in the W frame, or maybe said differently, the stress tensor in the bulk was 0. If you remember that. In terms of the properties of the quantum state, it tells you that these entangled Hawking particles A and B are in a they're in a maximally entangled pure state. So SA plus B is equal to 0, and SA is equal to SB, which is not equal to 0. It's equal to the log of the dimension of either A or B. Okay, so A and B are maximally entangled. That's postulate 1. Then there's postulate 2, which is unitarity, which is that if you look at the system after the page time, so somewhere here, then what happens is that the entropy of the radiation has maxed out. Okay. What this means is that or maybe said differently, it's the black hole is maximally entangled with the radiation. What this means is that the entropy of if you compare the entropy of R to the entropy of R plus one more quantum B coming from the black hole, then you should find that this combination here, the entropy of this must be less than or equal to this. Basically, because the entropy has maxed out, you cannot increase the entropy. And the claim is that these two postulates, postulate 1 and postulate 2, are in direct conflict, which is what I'll explain in prove on the next slide. Any questions? Okay.
Sorry, can I ask something?
Yes.
Yeah, I just got confused. So could you define what you mean by vacuum state at the horizon? I'm used to thinking of states defined on codimension 1 surfaces, so I'm just confused by the terminology.
Oh, I just mean, well, I mean many things. So let me start with the first one, that the stress tensor in the bulk is 0. Are we okay with that one? Or
oh, sorry, yeah, we're okay with that.
Yeah. So okay. So the stress tensor in the bulk is 0. There was a vacuum solution, and so on and so forth. Then we found what the quantum state was that led to this stress tensor, and we found that it was this thermal field double state, which was the state where the particle here is entangled with the particle here, and so on and so forth. And the statement is that this entanglement between these particles, and also between A and B, and so on and so forth, it was a necessary feature of that state, whose where the state where the expectation value of t is equal to 0. Okay. I'm saying that this entanglement here is sort of an if and only if. Or maybe I should draw it symbolically, with the expectation value of t equal to 0 in the bulk.
Okay.
Yeah.
Thanks.
Yeah. Okay. Any other questions? Okay. Yes.
Can I ask a question?
Of course.
It's a little vague question, but actually maybe I can ask it at the end of the answer. Sorry, it's directly related to this, so I think it would be a waste of time.
Okay, up to you. Okay. So this is the setup of the firewall paradox. So now let's actually see it in action. I've just rearranged things. So here's postulate 1, here's postulate 2, and we can just check that these two are in conflict by running them through strong subadditivity. Okay, so using postulate, so strong subadditivity is this statement here. You might have seen it in other lectures. It says that SAB plus SBR is greater than or equal to SABR plus SB. Okay. Now let's use postulate 1 to simplify this. So from postulate 1, this thing is equal to 0. from, also this term here has to be equal to S of R by postulate 1. Okay, because A, B are not entangled with R, so the state separates, and so the entropy will just be this. And then from postulate 2, or let me see. Yeah, from postulate 2, we know that this thing here is less than or equal to SR. Okay. Just simplifying, we would get S of R is greater than or equal to S of R plus S of B, which implies that S of B is less than or equal to 0, but entropy can't be negative, so that just means that S of B is equal to 0, but this contradicts postulate 1, right? Because from postulate 1, we have S of B does not equal to 0. The statement is that these requirements, the requirement to have postulate 1 and postulate 2 to both be true requires a quantum state that is not consistent with quantum mechanics. It's an impossible quantum state. It does not satisfy strong subadditivity. Just one comment about this is that this paradox is contained within a single light cone. So by this I mean a single sort of observer in the bulk, even though I don't know if I'm going to be able to draw it correctly, but a single observer in the bulk can actually collect all three systems and do the experiment and check that that the state indeed doesn't satisfy strong subadditivity. I guess I didn't explain this, but the reason why I'm making this point is because of this old idea of black hole complementarity, that maybe when black holes lead to when experiments on a black hole background lead to paradoxes, you can appeal to this notion that maybe actually no, let me say it slightly differently. Let's suppose that there's a measurement that you can do outside the black hole that conflicts with the measurement that you can do inside the black hole. Black hole complementarity says that, well, if you can show that a single observer cannot actually do or perform these two experiments before they crash into the singularity and die, then maybe it's fine. The law, it's quote unquote, it's okay to break the laws of physics so long as no single observer can actually check that the laws of physics have been broken. But the one punchline of the firewall paradox is that this paradox can actually be demonstrated by a single observer who collects the necessary quanta as they fall into the black hole. Okay, so there's something wrong. And so this sort of pits unitarity versus having a smooth horizon. And many people, well, it seems like it's an easy choice to make. If you want to break something, it's more sensible to break smooth horizon to preserve unitarity. And if you break the smooth horizon, this means that at some point along the horizon, you would, you break the entanglement, and this means that you don't have the vacuum state, and the stress tensor is not zero. And what this means is that you can have some excitations living on the horizon, which you can argue, well, well, okay, that's one statement. The other statement is that if it happens at any point on the horizon, using sort of the symmetries of this spacetime, the fact that you have reflection symmetry and a boost symmetry, this means that the entire horizon is actually on fire. Okay, so the entire horizon is on fire. And therefore, the wormhole is a lie. Any questions about the Firewall paradox?
I have a question.
Yes.
So once you invoke this firewall, are you just saying that the interior just completely disappears?
Yeah, well, that, at least when this idea was still fresh, that was definitely a possibility. That maybe yeah, space-time just simply ends at the event horizon of the black hole.
Okay. Just another question. So this type of firewall would I guess the initial reason you would think that you have a smooth horizon is you collapse some matter into a black hole, and then you sort of have a horizon which sort of looks like a Rindler horizon. So you would just decompose a Minkowski vacuum into two Rindler wedges. And then this firewall really only appears after the page time.
Mm-hmm.
But if you started throwing, like, let's say you threw in one particle before the page time, would you still get could you get a firewall before the page time if you did that?
No. If you throw anything in, if anything, you would delay the firewall by a bit.
But I thought in order to avoid the firewall, you need very special entanglement between the interior and exterior. And if you're throwing information in and it's getting scrambled, then you shouldn't expect the quantum state to have these fine correlations anymore.
Yeah, but except that, I mean, I'm drawing now a black hole formed from collapse. Here's the, oops. So you throw something in here. Yeah, what I'm trying to say here is that we don't understand, we don't have any, well, first, we don't understand what the firewall is. But it's not clear to me why throwing something in would create a firewall, right? I mean, how should I describe this?
I mean, the way I'm sort of thinking about it is initially you have sort of a product state between the black hole and this thing that you're throwing in. But once it gets close enough to the horizon, you can't really write the total state as a product state anymore because it's getting scrambled.
Yes.
So
but remember, I mean, the thing that led to the firewall is the fact that the black hole became maximally entangled with something else, right? So that's what happens at the page time. But throwing something in does not make the black hole maximally entangled with something else. If anything, it delays that because it makes the black hole slightly bigger. That's the thing that I'm trying to emphasize.
Okay, because the way maybe we can talk about it later, but yeah, maybe you can just continue and maybe we can talk about it later.
Okay.
You have, Ahmed, you have 5 minutes.
Okay.
Can I ask a quick question here? Sorry. If you accept the firewall, then doesn't that mean that you can't trust the computation that led you to the firewalls? You're just left with a big question mark.
Exactly. If there are firewalls, do we even trust that black holes evaporate? I mean, that's yeah. So that's a good question. There are other ways to argue for things like black holes evaporate and so on, but well, maybe I shouldn't try to go through those. But you raised a very good point. If there is indeed a firewall, should you trust everything that we discussed up to this point? So it seems like having a firewall invalidates having the firewall. So it's a big mess. And thankfully, the thing that we're going to talk about next time and the time after that is how to avoid it.
Thank you.
Mm-hmm. Okay. I wanted to make a quick comment about information retrieval. This is going to be extremely quick and schematic. So let's imagine the following thought experiment, where at some point you throw in, say at some point you throw in some particle M that's entangled. That's what this green thing, the green highlighting is supposed to indicate, with some external reference system D. Here on the left side, I'm describing sort of a toy circuit diagram for something like this, but it's actually it's for the case of an evaporating black hole. But the same lessons apply even in this case. But let me go through the circuit diagram. So if you look at the quantum state here, what this describes is W here is the wormhole or the black hole. It's maximally entangled with the radiation. That's what these things are supposed to indicate. And imagine that you throw in M into the black hole, which scrambles, and M is entangled with this external system D. After some amount of unitary evolution, some scrambling, you let the black hole evaporate for a little bit more, so you collect some more Hawking radiation. So that's what these two legs going into R prime are supposed to indicate. And so the final state is you have D, you have the new black hole, and you have the new radiation. Let's imagine you compute rho D W prime. You can do that by simply tracing out. That's what these red lines are supposed to be, tracing out R prime. So we're tracing out the radiation. Then you find a quantum circuit which looks something like this. And if we suppose that these U's have the property, that they behave like isometries. So I'm hoping that you guys have seen things like this in like maybe Walter's talks and Brian Swingle maybe. If this U behaves like an isometry, then this density matrix becomes the identity density matrix on the two systems D and W prime. What this is supposed to say is that so you throw your particle in, it scrambles. Then after some unitary evolution, the black hole W prime forgets about the message, right? There's no correlation or mutual information between D and W prime. The density matrix is a tensor factor. And a sufficient condition for something like this is for this unitary U to be a scrambling unitary. Scrambling unitary is a quantum circuit with length roughly log of the number of qubits, or number of degrees of freedom of or the number of input legs, or the dimension rather of the input legs, and where at every time step a different order 1 collection of at every time step there's a random sort of k-local unitary transformations coupling k, or let's say 2 of the qubits at a time. So like something like this. So at this time step, you get something like this. At this time step, you get something like this, and so on and so forth. Okay. If this length here is log of the number of qubits, then it would satisfy this requirement. Okay, I'm going very quickly. Let me just make my final point, and then I'll take questions. The final point I wanted to make was that this is about the information paradox and why it arose. The statement that it's a paradox is a statement. It's because we were looking at essentially the calculation that we're doing looks at something that looks at something like this, where we're looking at some given space-time geometry, some saddle point, and the statement of the information paradox is that the corrections to the saddle point are small, and so they won't change the result by much. And so the only thing that can fix things is that maybe there are other saddles that can somehow compete with the first saddle. Even though quantum gravity effects are small, there is something that's growing. Entanglement is growing. So perhaps due to this growth of entanglement, one would get an exchange in saddles. Or maybe I say differently, that the saddles would exchange dominance. So we would get the phase transition. I guess in this case, it's a first order phase transition. And this is what we're going to talk about during the next lecture. So that's all I had. Thanks for your attention.
Excellent. All right, questions? Yes, Stefano.
So this is the big question I was about to ask before. And so to derive the paradoxes, both the Firewall one and the other one, it seems to me that, I might be wrong, but it seems to me that you relied on factorization of the Hilbert space in gravity. And I heard other points of view where this assumption factorization of the Hilbert space might be a problem, in the sense that there are, as you said, small corrections, but those small corrections might lead to an order one effect, in the sense that maybe when we compute the entropy of the black hole, we don't take it, let's say, because a typical state in the Hilbert space looks thermal up to exponentially small corrections. And so if we don't track those exponentially small corrections, you might not be able to detect the fact that you are actually in a pure state instead of a mixed state. So that's one thing. And the fact that we assume factorization of the Hilbert space, which is true probably up to exponentially suppressed corrections, might be enough to not have a well-posed paradox. So I wanted to know a little bit what's on this discussion that is around, what's your point of view?
Yeah, that's essentially what I'm going to be talking about next time. The statement, the statement of having a factorization of the Hilbert space in position is true so long as this saddle point dominates. So long as you well, yeah. So it's so long as you can justify that the saddle point is the dominant one, then I think that assumption is valid up to very small up to very small corrections. But the thing that we're going to discuss at length in the next lecture is that new non-perturbative corrections from the gravity path integral violate this tensor factor structure for space that we've been assuming, and which led us to all of these problems, the information paradox and the firewall paradox.
Okay, I understand this idea where you include these non-perturbative contributions, but in general, okay, you mean that it factorizes up to sub-leading corrections, because anyway, even in that, when that saddle point, the saddle point we are analyzing dominates, then also in that case, you have some non-factorization due to the fact that observables in quantum gravity are probably no local, and you have to address them. And so in some sense, you have some non-factorization effect at sub-leading orders, and you're claiming that those are not enough to resolve the paradox?
Correct. So there are two kinds of non-local effects. There's the very mild version, which is so non-locality due to dressing. I would call those mild, and those are they're like this thing. They don't change the results by much. But the thing that I'm talking about is it's kind of weird. It's non-locality due to complexity. Like it depends on which observable you're trying to compute. So suppose you want to compute something like the commutator between O1 at X and O2 at Y. Okay, and you're trying to compute the expectation value of this, or maybe you want to compute the thing squared or whatever. If these O of X and O of Y were just like local operators, just like local fields, then when you compute this quantity, this commutator, this first saddle point dominates, and you get a result which is 0. That points space like separated commute up to these simple dressing issues. You can always dress things so that things commute. But if these O's are complicated, or at least maybe one of them is complicated, and what I mean by complicated, that should become clear in the next lectures. It's like where it depends on the density matrix, or rather, where the operator, the way you formulate the operator, it contains within it a gravity path integral. So you can formulate the operator using the gravity path integral, and then that can create wormholes. And then you'd find that other saddles to the calculation of this expectation value dominate over the first saddle, and will give you an answer which is not 0, even though naively it looks like there's space like separated. Hope that answered the question.
Yes, thank you.
Very good. Elliot?
Yeah, I just had a short question. So could you just go over your argument why if we have a firewall at late times, then some symmetries imply that the firewall is everywhere?
Good. So first I'm gonna have to erase this amazing piece of artwork. Okay. Let's suppose that the firewall kicks in at some time. Let's say this is like the page time or something. Okay, the firewall kicks in. Then there's fire everywhere in the future here. And by fire, I just mean that the physics, the future of this point, we don't understand. It doesn't have to be restricted to this line. Now, this system has a boost symmetry, right? So I can boost things like this. But if I apply this boost, this point here just moves down. It gets closer to the bifurcation surface. Okay, so this proves, or it's an argument that this entire future horizon here is singular, and also to the future of it, like everywhere here. But there was nothing special between the left, if there's a firewall on the right-hand side, surely there should also be a firewall on the left-hand side. So this means, this means that we should also have by the same argument, we would say there's a firewall here, but then by the boost argument, we would push it all the way back and say we have a firewall everywhere in the future wedge. Well, a firewall along the horizons, and so the physics in the future wedge is not determined. Or maybe it's just not there. But there's also, there's a symmetry here between evolving to the future and evolving to the past. So this means that there's a firewall here. And by the reflection symmetry again, there's a firewall there. And again, we can boost this all the way up to the bifurcation surface. And so then we would say that we also have the physics inside this entire region is in doubt because of the breaking of the entanglement and the firewall that can be pushed all the way down to the bifurcation surface. Did that make sense, or was that too quick?
Yeah, no, I think that makes sense. I'm just wondering, how much does this rely on the fact that the black hole is eternal here?
Very much so.
Okay, right. So for like an evaporating black hole or something like that, you would not necessarily have the same conclusion that holds.
Correct. For an evaporating black hole, the most reasonable expectation is that it should kick in at the page time, if the firewall actually exists.
Okay.
But that's it. But you can't evolve it backwards.
Right. Yeah, that makes sense. Okay. Thank you.
Mm-hmm.
And just to follow up, I mean, on that last comment, the page time thing still assumes that somehow by that time the black hole is reasonably quasi-static, right? It can't be evolving dynamically in the sense that you don't really know where the event horizon is.
Sure. Well, yes.
Okay. Great. Other questions on the recorded part? Okay, so if not, let's thank Ahmed again. And we can stop the recording.